Pleasure to be here. I'm sorry that I couldn't be there in person this week, and I really appreciate KITP enabling the remote attendance and presentation at a meeting since travel just turned out to be impossible. I also appreciate everyone coming out to hear about star formation histories of galaxies near and far. We'll talk today about a number of different topics. I've started with my conclusions just so you see what's coming and can decide which parts of the talk you'd like to stay awake for. We'll talk about spectral energy distribution fitting, in particular the dense basis method of star formation history reconstruction, which provides a powerful tool for probing galaxy evolution. And hopefully this will help set the stage for Kartik Iyer's talk tomorrow. We'll report on recent results led by grad student Charlotte Olson, where we found synchronized star formation in local volume dwarf galaxies and evidence for galactic conformity in a mixed sample of local group and local volume galaxies. And then I'll switch gears and talk about Odin, which is a high redshift Lyman alpha emitter survey using narrowband imaging on the dark energy camera, and how Odin early science includes studying the spatial clustering of objects, as well as back to star formation histories for now these high redshift Lyman alpha emitters. The folks involved who deserve all the credit are the researchers, members of my research group, and collaborators. You'll see many of these names as we go on, especially Charlotte's, who I mentioned. Let's review spectral energy distribution fitting for a moment. We use the integrated light from galaxies because it contains a lot of information about both their present and their past. We can use it to find photometric redshifts. Even if we know the redshift, we use SED fitting to find the stellar masses, star formation rates, metallicities, dust properties. And we infer these properties by forward modeling the observed spectral energy distributions, which of course are not usually sampled at such high resolution, but spectrophotometry can be used, via stellar population synthesis models. We can learn about the young stars, how old the stellar population seems to be, and more than just a single value of age, as I will show. Interstellar medium through the nebula emission lines, the old stars that are the bulk of the stellar mass, and if we can measure far enough red wavelengths, the re-emission from dust. Spectral energy distribution fitting has traditionally assumed simplistic star formation histories. What's shown here is a realistic star formation history from TNG 100 and an exponentially declining model. These are still widely used. You'd either fit a constant star formation rate to this, or it has to have zero star formation from the Big Bang until some moment when it starts and then exponentially declines. This is not satisfactory for the vast majority of galaxies' actual star formation histories. So we want a physical non-parametric star formation history that is a smooth curve where the number of features increases with the quality of the data to get a decent fit to the star formation history. Even though we don't observe this, we observe the spectral energy distribution. That's been achieved with the dense basis method through the use of Gaussian processes. And there are other flexible approaches out there that use flexible star formation histories, including the ones I've listed here. So let me tell you a little bit more about how dense basis works. We want our star formation history to be physically motivated. That is, it shouldn't go negative or have discontinuous derivatives, which happens if you put things into bins. We want to encode the maximum amount of information with a minimal number of parameters. We want to see a correspondence between the goodness of fit in the spectral energy distribution space we actually observe, and then a goodness of reconstruction in the star formation history space. We validated that carefully through simulations to make sure that a good chi-squared here implies that you've done a good job here. The example shown here looks pretty good. We don't get every little up and down of the input star formation history, but we reconstruct its broad features. And then as you see in the dimmer black curves, we've actually sampled from the posterior to give you a sense of the uncertainties on the star formation history at each point in time. We use a flexible parameterization with a tuple, and that tuple includes the stellar mass, the instantaneous star formation rate, and then the look-back times at which a galaxy formed different fractions of its stellar mass. The Gaussian process allows us to create smooth star formation histories that satisfy these as integral constraints. Having a flexible number of parameters lets us specify the star formation history to better precision for better data, hence it's a non-parametric approach. And it can be incorporated into any SED fitting code. There is a public version of dense basis that's parallelized and extremely fast. Here's an illustration of what we're talking about with star formation histories. T25 is the look back time, looking back from the present, in this case for a galaxy at redshift 1, so the Big Bang is here, to when it formed 25% of its total mass. T50 is when it formed half its mass. You can figure out what T75 is. That's the basic idea. That would be 3 Tx parameters in our tuple, along with stellar mass and star formation rate. But we can vary that number of parameters. So here's an example of what you get with it fitting with a Gaussian process, one of these realistic star formation histories, using one parameter. It's just parameterized by T50, the total stellar mass and the instantaneous star formation rate. If we up to more parameters, 2, maybe it doesn't do much better. But in this case, 3 does quite well. And so you'd expect a good chi-squared. Do we need more? Well, even if we go to 5 parameters here, the fit doesn't get a whole lot better. So we'd expect a reasonable stopping criteria, like the Bayesian information criterion, to prefer 3 for this particular case. As a reminder, what we're doing here is in spectral energy distribution space. That's where our data are. We're fitting for star formation history parameters that I've just described simultaneously with models for the dust, metallicity, redshift if it's not known, nebular emission, intergalactic medium absorption, etc. This is a complex, high-dimensional problem. Most of the progress we've made with star formation histories has been to make standard assumptions for the nature of the dust law, the nature of the metallicity, etc. And what do these star formation histories tell us about galaxy evolution? Well, we get more robust values for star formation rate, stellar mass, and then instead of a single age parameter that's often overinterpreted, we can actually report the Tx values and their uncertainties. We can probe the number and duration of major episodes of star formation in galaxies past, which you of course cannot do by assuming a constant or exponentially declining single stellar population. We can probe the evolution of scaling relations, like the star formation rate, stellar mass correlation, the timescales of morphological transformations, the stochasticity timescale for a whole bunch of galaxies. That's something Kartik's been working a lot about and may talk to you more about tomorrow. And the constraints on feedback processes that regulate star formation via comparisons with simulations, in which I know there are many experts in the audience. Here's a recent discovery enabled by the dense spaces star formation history reconstruction. Moving on now to the second phase of the talk. This is a paper led by Charlotte Olson about star formation histories probed with both spectral distributions through the dense spaces method and color magnitude diagrams, fitting star by star and resolved stellar populations. We find that those methods agree, and we found that they both illustrated evidence that there is synchronized star formation in local volume dwarf galaxies over the past 3 to 6 gigayears. And this is what we found. So if you basically look at the black curve initially, these are the binned color magnitude diagram-based star formation histories, taking a median over the entire sample of Angst dwarf galaxies in local volume, and then using the 68% scatter to get an uncertainty on each. So the star formation rate was high and dropped and then rose again. So we had a period of quiescence across the local volume without a lot of scatter in that from 3 to 6 gigayears of look back time. When we took that star formation history in the black curve and input it to make a mock spectral energy distribution, and then analyze that with the dense basis method, that produced the blue curve here. So that shows that there's a roughly 1 gigayear systematic offset in our SED fitting versus what for that moment is assumed to be the truth from the color magnitude diagrams. Then we took the observed integrated photometry for the Angst galaxies, independent of the color magnitude diagrams, ran the dense basis on them, reported the median star formation history with scatter, and that's shown in the red curve. That red curve is so similar to the blue curve that we see no evidence for any disagreement between these two methods. And while we may have a 1 gigayear offset in the timing, both methods agree that there's a decline in star formation rate in local volume dwarf galaxies several gigayears ago, which might, due to uncertainties in the ability to time the age of very old stars, actually correspond to an earlier epoch around randomization when dwarf galaxy star formation was expected to be reduced. And then we see a rejuvenation around 2 to 3 billion years ago, when the median and most of the galaxies in local volume started forming stars heavily again. This kind of large-scale coordination is not predicted by galaxy formation models, and remains a fascinating mystery to see why it's happening in the local volume. Now, we were initially skeptical about this. So one of the great things that Charlotte did was additional tests including breaking the ink sample into different sectors of specific star formation rate and finding that the median star formation history still looked quite similar, except for the most recent time bins. And then investigating further by breaking the local volume into 4 regions surrounding the local group, shown here. And then here we're showing for the CMD-based star formation histories, the median and scatter in each of the 4 regions. Those regions are compatible with each other, except at very recent times. And in the dense basis fits. Again, the 4 regions are all quite compatible with each other, with a bit of disparity for the instantaneous star formation rate. So this is not being dominated by any one region, and we found the result robust enough to publish. As a follow-up project, Charlotte worked on searching for galactic conformity in now a combined sample in the local group and the local volume. For this, star formation histories used were just from the color magnitude diagrams, because it's impossible to get good integrated photometry for SED fitting in the local group. We found that when splitting on the central stellar mass, or specific star formation rate, there's conformity for secondary galaxies. This is basically, you start at a primary, which is an isolated central, and then you look at the distance to all other galaxies in your sample and measure their properties. And finding these indications of conformity here and here, that it actually makes a difference, implied that secondary galaxies separated by 2 to 3 megaparsecs from high stellar mass primaries are more likely to have high star formation rates. The same statement holds for secondary separated by 2 to 3 megaparsecs from low specific star formation rate primaries. This is another intriguing large-scale coordination, but it doesn't appear to be the same one as the synchronized star formation, and I'll show you why in a moment. First, I want to show you that one of the neat things we were able to do, because we're using star formation histories, is conduct the first probe for galactic conformity looking backwards in time. We did this test 1, 2, and 4 gigayears ago as well, with all the star formation histories, but there was not statistically significant evidence for differences. However, when we split the sample based on the quenched fraction, we found that at look-back times of 1 gigayear, there was an important difference. And so the conclusion here is that secondary separated by, again, 2 to 3 megaparsecs is a very interesting distance band from low stellar mass, actually in this case, from the higher quenched fraction primaries are more likely to be quenched. So evidence for a different kind of conformity 1 billion years ago. What should we make of all this? Well, we wanted to be careful about this. And so we did a lot of further tests to ask, is this signal found in the galaxies with synchronized star formation? Those were only in the local volume. Maybe we're seeing the cause of that synchronized star formation, we thought. So we repeated the same test with only the local volume. This is the signal we had before, and this is what it looks like if you take out the local group. The whole signal goes away. That signal is being caused by local group to local volume pairs with a 2 to 3 megaparsec separation, and predominantly by local group secondaries to local volume primaries with that separation. This leads to a lot of questions. In particular, it appears the conformity signal is sensitive to the geometry of the region we're examining. One of the frustrating things about the local group and local volume is it's not easy to probe further out to get similarly sized volumes to see if not having the admittedly weird local group at the center would still generate a signal at 2 to 3 megaparsec separation. And so for her next act, Charlotte has accepted an LSSTC Catalyst Fellowship to go to the City University of New York and continue this investigation using the LSST data sets in the deep drilling fields to expand the local volume and get a larger sense of whether this conformity signal is happening in other regions of our nearby universe with the same geometry. And here's the published paper. Okay, let me switch gears for the final time and talk about the 100 square degree DECAM imaging in narrowbands using the dark energy camera called Odin. The goals of Odin are to find over 100,000 Lyman alpha emitting galaxies at registers of 4.5, 3.1, and 2.4. Also to identify over 600 galaxy protoclusters, both Coma and Virgo progenitors in mass, via strong overdensities in the angular distribution of the Lyman alpha emitters, and to find hundreds of Lyman alpha nebulae, affectionately known as Lyman alpha blobs, from their diffuse emission. To do this, we built 3 custom narrowband filters that were large enough to fit the wide field dark energy camera and its 3 square degree field of view, and centered them at the right wavelengths with relatively narrow full width half maxima to find Lyman alpha at these 3 redshifts. But we still needed to get 3 months of observing time on the dark energy camera to make this work. That we were fortunate enough to be awarded a NORLAB survey for that purpose. The project is led by Kyung-Soo Lee at Purdue. And the 3 filters that we built are shown in red here, corresponding to ages of the universe since the Big Bang of 1.4, 2.1, and 2.8 gigayears, so nicely spaced for an evolutionary study. As a reminder of how we select Lyman alpha emitters with narrowband filters like that, here's a diagram with a narrowband filter, a Lyman alpha emitter template, and then neighboring broadband filters. And if you look at a postage stamp of a galaxy, and you see for a typical object that it basically disappears or gets noisy in the narrowband filter. But the object that's centered here actually looks brighter in the narrowband filter because it has more flux density in the narrowband filter than in neighboring broadband filters, and that's because there's a strong emission line triggering that narrowband filter. We have techniques to avoid interlopers from other emission lines, including requiring a high observed equivalent width and using color filters when needed. And this is what the HST images of some of our Lyman alpha emitters that we found in the past look like. Early irregular galaxies caught in the act of formation. When we look at the sky distribution of Lyman alpha emitting galaxies in early Odin data, we've done this at all 3 redshifts so far. These 2 are in the Cosmos field. This is in the Deep 2-3 field. We use HyperSubPrimeCam, Super Strategic Program, DR2 imaging for our broadband imaging, and our narrowband images taken on the dark energy camera, the narrowbands. And we get roughly 5,000 Lyman alpha emitter candidates per field. So these are unprecedented sky densities and sizes of samples at these redshifts. We're also going to address a related question. And some of you might recognize this slide if you attended the longer duration galaxy evolution workshop and saw my review on galaxy scaling relations. So here's the star formation rate stellar mass diagram for many different types of galaxies, and for Lyman alpha emitters in the blue points, they seem in one group's analysis, which I happened to work on, to lie above the star formation rate stellar mass correlation. But there are other papers in the literature that claim that Lyman alpha emitters lie on the star formation rate stellar mass correlation. So this is one of these mysteries about galaxy evolution that I think we have to resolve. Maybe it's not a mystery, but rather systematics of one form or another. So within Odin, our plan is to approach this very cautiously and to use the dense basis star formation history reconstruction method with a flexible dust law that we apply identically to Lyman alpha emitters and the continuum selected galaxies in the candles fields where we have good broadband SEDs all the way across, and to determine for sure where the Lyman alpha emitters lie on this overall diagram. And that leads to my conclusions. With a careful analysis of the spectrum and distributions of galaxies, we can reconstruct their star formation histories and probe galaxy evolution. We looked in the paper from 2021, led by Charlotte Olson, at correlations between local volume dwarf galaxies and found synchronized star formation features not predicted by galaxy formation models at 3 to 6 gig years look back time. We then looked in a 2023 paper led by Charlotte for the star formation histories of local group and local volume galaxies and found signs of conformity that were independent of synchronized star formation. And we're waiting to find out if we can illustrate if that's really just something special to the local group or something that happens in other similar geometry volumes of the universe. And then I've talked about Odin, using the dark energy camera to obtain unprecedented samples of Lyman alpha emitters, Lyman alpha blobs, and protoclusters in 7 well-studied fields covering 100 square degrees across the sky. Our early science involves analyses of the spatial clustering of all these objects, including cross correlations, as well as the LAE, Lyman alpha emitter star formation histories that I just told you about. I appreciate you listening, and I'm happy to take questions.
Thank you so much for the talk, Eric. Do we have any question? And as a reminder, please say your name for the people in Zoom before you ask the question.
Sucheta Kure from Nagoya University. Thanks for the really nice talk. So I was wondering, in your LAEs and protoclusters of Redshift 4, do you have quenched galaxies in your sample?
That's a really interesting question. It's difficult for us to select them. So we are doing Lyman break galaxy selection along with our Lyman alpha emitter selection, and including Lyman break galaxy candidates on spectroscopic follow-up. We just had a night on Keck Demos for this, and we're starting to reduce those spectra. The quenched galaxies can be found as Lyman break galaxies,
Right.
but if they're very red, they will usually fail the Lyman break galaxy selection criterion. So we could try to do something further where we use spectroscopic redshifts that exist even if they don't meet Lyman break galaxy criteria. I don't think we've included those yet in our spectroscopic follow-up. I mean, inevitably there will be quenched galaxies. It's just not a sample that we're well set up to select.
Right. It would be interesting to find protoclusters with these like quenched galaxies that's happening at high.
I see your point. So, you know, we don't expect heavy quenching in the protoclusters.
Right.
But of course, they are the most evolved regions of the universe at any given epoch. So it makes sense to look for the quenched galaxies as well. One thing we can do, of course, is once we've identified the protoclusters, then do a study of the properties of galaxies at the right photometric redshift there to see if they looked quenched and put slits on them for spectroscopy. So maybe that's the best approach to your very welcome suggestion.
Okay, thank you.
Right, and we have our second question.
Hi, Eric. This is Martin Ray. Really interesting talk. I was wondering whether you had any ideas of why and what could be causing the synchronized and conformal star formation histories in the local volume. This is a very large volume for very tiny galaxies. So what do you think is correlating them on such a large scale?
Right. I'm going to answer the question in different ways for the two phenomena because they've turned out not to be related to each other. For the galactic conformity, we really have no idea. That looks pretty strange, and it may turn out to be just a feature of the weirdness of the local group when it happens to dominate pair counts and bins. But of course, we don't know that yet. For the synchronized star formation, there are a couple of ideas. One is that this is something universal. You'll see this in all such volumes of the universe, because the ionizing background radiation became diffuse enough around a redshift of 1 to 0.5 for star formation to restart in these dwarf galaxies. This was actually Greg Bryan's suggestion. So we can test that by looking for this phenomenon elsewhere. The other would be something more localized, where it turns out that the local group was on a moderately sized filament, and filaments can cause synchronized galaxy collapse. And that might have triggered the rejuvenation. I think it's unclear, but comparison with simulations to find out how often these effects are seen in volumes like a local volume would be a great way to tell us what seems to be causing it.
Thanks. So just to follow that up quickly, what's the stellar mass, the typical stellar mass of the dwarf sample where you find the synchronized star formation histories?
Right. They're often around 10 to the 8th to 10 to the 9th.
So you, I don't know, would you expect the UVB to play such a role in regulated this kind of massive dwarfs?
That's not what I'm an expert on.
Okay.
You're
Yeah,
skeptical, which is making me more skeptical.
Okay, thanks.
Thank you. Do we have any other question?
Yun Chong Wang here from Stanford. I want to also follow up on the second point. Do you see any correlations between these rejuvenated dwarfs in the local volume and say with their host properties, with their distance to the hosts, or are they all in the field? Can you comment on their environment? Thank you.
Great. Yeah, I really like that question. It's a good line of thought. So in general, the way to test that, I think, is to go to the conformity tests, because that's when you're using the distance between centrals and the secondaries, which can be either centrals or satellites. and looking for variation in properties. And there we're not seeing anything even in the one halo regime where conformity is expected. So I don't think we can say anything strong about that except for these couple of intriguing but mysterious conformity signals we've reported.
All right, so let's thank Eric again. And